So Kidmin, are you recording? Okay, great, great. All right. So yeah, let's look at so today's content. So we'll be mainly looking at the systolic array. So the first one we'll be looking at the systolic array, and then how do we verify it like in the access stream way, right? So how do you have build a access stream randomized test bench, and then the systolic array is firmware, and and finally like the end-to-end verification setup, and we will see like how you can also replicate the same behavior, right? And yeah, and then I'll also talk about how you can put your own module into, you can fork our repo and you can put your own module into this, and that way you can easily get like everything end-to-end running. Okay, all right. So let's talk about systolic arrays data flow. So maybe like can you raise your hands like if anyone knows about like systolic arrays already? Like I mean, if you know how they work and all. Okay, great. All right. So I'll give like overall sort of introduction. Okay. So the idea of systolic array is basically it is a like a fast way of doing like matrix multiplication. So fast in the sense um so it's basically a type of accelerator, right? A systolic array and for matrix multiplication. And it is not a very new idea. It has been there from 1980s. But then with the AI and all, so now most of the AI's inference operations can be written as matrix multiplications. So that way, because of that, now like in the last about 10 years, like there are like ton of AI accelerators out there, and many of them they follow the systolic array architecture because it's a very simple and a very performant way of building it, right? So the systolic array is the most popular AI accelerator architecture now. So for example, Google's TPU is a very large systolic array, right? So, and they are very good at doing matrix multiplication, and sort of like the only thing kind of they do is like matrix multiplication, right? So it is, if you want to do convolution or if you want to do anything else, then you have to like make those into matrix multiplications, and then you have to give it to a systolic array, and that way you can do a matrix multiplication and like do it faster. Okay, right. So let's see how a systolic array works. So what you have here is basically the systolic array, this part. Okay. So I searched for some good animation. So I mean anything that can show the data flow through the systolic array, but I couldn't find anything. All right. So it is not like super hard, but I mean it might be a little counterintuitive. Okay. So all right. So this is the systolic array part. So the reason it's called systolic, it's because the way that data goes through the systolic array is similar to how, or it looks like how data flows through like your heart, right? The systolic and diastolic rhythm, right? So, right. Okay, so the key idea here is basically now let's say you have two matrices, right? So you have a matrix A and you have matrix B, okay, and matrix B, and you are multiplying these two matrices together to form this matrix C, right? So let's mark the dimensions. So let's say a matrix A have say R number of rows. Okay, so R rows, and the number of columns. So we'll say like it has K columns. Okay, and B has basically C rows. Oh no, okay, K number of rows and C columns. Okay, and the output matrix has basically R rows over here, and it has C columns. Okay, so you can see this R into like R into K matrix, and you multiply that with K into C matrix, and you get a R into C matrix. So this is the standard matrix multiplication, right? So that is, let me write it here. So R comma K are the dimensions, and this is K comma C are the dimensions, and the output is basically R into C. So I should probably use a different letter for this. So let's say, I mean, O whatever, okay, something. So R into C, right? So like the idea of matrix multiplication, right? So what we do is basically you take say you take this and you multiply with this, okay, and that becomes the first one, okay. And so similarly, what you take like the same thing, and then you multiply with the second one here, and that becomes this, okay, and you multiply with this, and it becomes this, and you multiply with this, and it becomes this, right? So and you add them together, right? So yeah, so this is the like the general like the idea of matrix multiplication, right? So now the question is like, how do you like sort of like accelerate this, or how do you like do it in parallel, or like using multiple like elements in parallel? So how many operations are there in matrix multiplication? So if you take the number of operations, it's basically R into K into C. That is, if you take multiplications, right? So the total number of multiplications is R into K into C. Like multiplications are there. Okay. Why? Because you are multiplying this one with this one. Okay. So that will give you K number of um, like multiplications, right? So you are multiplying each of these 1, 2, 3, 4 into 1, 1, 2, 3, 4. So that gives you K number of multiplications. And by doing that, you get this one output element, right? So sorry, by doing that, you get this one output element. Okay. By multiplying these this K and this K elements together, you get one. So you to get one of these, you get K number of multiplications. How many such elements are there? You have R into C such elements, right? R columns and C R rows and C columns in the output matrix. So you have R into C such elements, and each element needs K multiplications. So totally you need RKC number of multiplications, right? So now, okay, so let's say like we want to parallelize this, or like we want to do this through accelerator, right? So in a systolic array, you basically have R into C times elements. So in this dimension is R, okay? So in this dimension, you have R, and in this dimension, you have C, right? So this systolic array basically maps to this output matrix. Okay, like so of 1-to-1 maps to the output matrix. Okay. So what you have here is the output it maps to the output matrix, R rows and C columns, right? And yeah, so the idea is like over K number of clock cycles, okay, or else like by sending data in like K number of clock cycles, you can multiply this all of this together and get the output, right? Okay. So okay. So the next part is basically how do you like send this data, and how does this work, right? So what you do is you send this matrix A through here. Okay, so matrix A is sent through here. And you can see this corresponds to the R dimension, right? So R dimension. So you are sending one vector at a time, right? So each vector is the dimension of R. Okay, so R number of elements, right? And you are sending that in every clock cycle. So that's why you have say this is 0, 1, 2, and this is r minus 1, r minus 1. Okay. So, and you are sending all this entire vector at once along here. Okay. So similarly, like on this side, you are sending the matrix B, and you are sending this one column at a time. Okay. So you basically send this column at a time. Okay. So, and you send say like 0, 1, 2, and C minus 1. Okay. And then you are sending this, all of this inside, right? Okay. So now you see, like when you send like that, now this and this, they both reach here in the first clock cycle. Okay. So these blue boxes are registers. So you are delaying this by 1 clock. You are delaying this element by 2 clocks. You are delaying this element by 3 clocks, etc. Right? So this element and this element, they both reach the first one in the first clock cycle. And what you do is basically you multiply them. So this is the internals of it. Okay. So what you have here is the internals of a one processing element. Okay. So you can see this one. This is the matrix A, and this is the matrix B. Okay. So you are multiplying the elements over here. So you get this and you get this, and you multiply them and you add them, and then you put them in a register, right? So you multiply this one and this one over here. Okay. And yeah. So, and then like in the next block cycle, you'll be sending the next row here. So that is next, yeah, next column. So that's like next set of rows. Okay, these ones. Okay. So like this. And here also you are sending basically, yeah. So you are sending this first, maybe. And over here you are sending, you're sending this one first. And then like the next clock cycle, you are sending this one. So similarly, on the B matrix side, you are sending this, right? And in the next clock, they both go there and they get multiplied and they get accumulated. So, and here you have a register in here. So that is this accumulator register, which adds all those values, right? So, okay, right. So if you look at this, this matrix, so like, okay, this first element basically that corresponds to this one. Okay. So to get this data, we need, you have to add this, and this, right? And similarly, you have to add this, and this. So you can see both are this k dimension. So over k number of clock cycles, so the k clock cycles are here. Over k number of clock cycles, these multiplications happen, and you get accumulated together, and you get this one value k. You get this one value for the like the 0, 0 value over here. Okay. So that is the like basic idea. So, and that is the first one, right? So now the thing about systolic array is basically it is designed in a way that it can be placed and routed easily. Like when you go for FPGAs, or like especially when you go for ASICs, right? So the idea is like, I mean, yeah, so it can be placed and routed easily. So the way that it happens is now the in like the data you send here, X, or like the this value, that goes and like it get registered over here for one clock cycle. So inside here you have a register which holds this k value that goes from the top. Okay. So you hold it for one clock and then you send it to the next one. And that becomes the input for the next, this element. That becomes the input for this element. So from the top, you are sending weights downwards. And from here, you are sending, say, inputs this way. Inputs and weights. Okay. So, and that happens in following clock cycles. So now this gets the first element in the first clock, and in the next clock cycle, this element has gone here, and that will get multiplied by the second element from here. Like I mean, or the okay, that gets multiplied by the first element here. So now you can see this column. This column directly gets mapped into these four values over here, right? So the first one doesn't have any register, so that goes straight in the first clock cycle. So the second one has a register, so that gets delayed and it goes in the second clock cycle, right? So when the second one reaches there, you can see that this one has gone through this register and now it is available over here. So there, this value from here and this one, they both meet in the second clock cycle and they get multiplied and they get accumulated. And similarly, like when it goes here, now this has been delayed by 2 clock cycles. So it meets them at the same time and they get accumulated. And this gets delayed 3 times and they get accumulated, right? So this way, they basically like all of these are delayed by 1 clock. So that way, like they all meet at the different times. And that way they get multiplied and accumulated at the right time. Okay. So the order, I think like first we will look at this, how this one looks like in Verilog. Okay. So I think that would be pretty straightforward. So let me see. Okay. So this is the PE, the processing element. So we'll look at that one first. And yeah. So you can see let me clear these things maybe. Hmm. Let me see, there's a question. Let's see if we can answer that. Okay. Is the number of inputs equal to the number of clock cycles? Yes. So basically by inputs, if you mean the k dimension, so that is this along this k dimension, okay, which is the common dimension in both sides, that is equal to the number of clock cycles. So like that is the number of times like you will give these inputs. Okay. All right. So let me clear the drawings and let me show you this. Okay. So you can see like there is a register process clock, and then we put this KO is the output, that KO out, and then we delay like that by you have the input delay by 1, and similarly X out you delay it by 1. Okay, right. And at the same time we also have this like we have a separate register here. So let me show that. So it is not shown here. So that is a separate register that would be somewhere here. Okay, right. So, and this register is the RO. Okay, and we are copying this accumulator value into the RO. So we'll copy only when like, I mean, this R copy signal is enabled. Okay. So, and then like, I mean, we have another one that's called the shift signal. I'll talk about that later. Okay. So this is inside a PE. We basically have this multiplier and accumulators. So basically, that is the MAC. So if you look at the MAC over here, okay. So I'm doing a multiplication of the X and K, these two values, and then I'm delaying it by this LM minus one. So that means LM means latency of the multiplier, right? So the design that we have is basically designed to have a parameterizable latency. So that means like the multiplier you can have like a different latencies you want. So you can have 1 clock latency or 2 clock, 3 clock, right? So the idea is like basically you can change the processing element from say fixed point like an integer multiplier to a floating point multiplier or like any different data type or whatever you want. Okay. So and let's say like you switch it to floating point, then you need a higher. You might need like multiple clock cycles to do the multiplication, right? So because you need to retime the design and everything. So you can change the MAC unit like only without affecting anything else. Okay, so that is the idea that we have. So you can delay. So this is like parameterized. So because it's an integer, you can sort of do it in 1 clock cycle. And to sort of test the whole design and like make it sort of to stick with the idea of parameterized latency, I'm delaying the output of this by LM minus 1 clock cycles. Why this is done in 1 clock, and then if I delay it LM minus 1, the whole thing is delayed by LM clock cycles, the latency of multiplier, right? So similarly, like this is the accumulator, right? So the accumulator, you take the so what you have is basically you have the M. So M is the output of multiplier, and that is added to the A result. A result is the accumulator. So it gets added to the A result, and you keep adding it into the A result again and again and again, right? So, but then you want to clear this accumulator, okay? So you clear this accumulator like when you get this M first signal, right? So if you get the M first signal, you add it with 0. So that is you're adding a set of numbers. And if you're adding the first number, then you basically add with 0 and put in the register. If it is not the first number, you add with the register itself and put in the register, right? So that's why this behaves as a like accumulator, right? So this M first tells whether this particular value is the first value or not, and that is an input. And I'll tell you how we calculate that as well, right? Okay. So this way, like you keep accumulating into a result, right? And then the result of a result, although like I delay it by LA minus one, that is latency of accumulator minus one. So that way, the whole latency of the accumulator is like LA, that is latency of accumulator, right? So and then you send the data out. So this is the multiply accumulate module, right? So and this basically abstract these two functions. Okay, so the reason I have like put this as a separate module is basically if you are changing this data type, then I can only change this module itself. So for floating point or say MX types or something, and without affecting anything else. All right. Okay. Do you have any questions in this within the processing element? Okay. So if not, we can move on. And okay. All right. So to summarize that, basically we have this. Mm, so we have the multiple accumulate unit, and also within a processing element, within a PE. Okay. So within the processing element, we also delay the input weights and inputs by like one clock cycle, right? And send it out. And this becomes the input to the next processing element. So the next processing element will sit here, and the next processing element of this will sit here, right? Okay. So let's see. And yeah, okay. So when the data goes to this one, okay, and we basically take it and do the same, like we multiply and send it out and all that. So now there's a like an interesting pattern that we can observe, right? Like in this whole thing, okay. So that is now this processing elements gets the data in the like say 0th clock cycle, or like as soon like I mean as soon as the data comes in immediately without any delay, this processing element gets the input and k, right? So x and k, and it can do the multiplication, right? So and it takes one clock cycle, and after one clock cycle these two elements will get it. Okay. So the same input and same x and k, these two elements will get them. Okay, the same order of x and k, and then like in the next clock, they will get the valid data. So like we are tracking which are the valid data here. Okay, we are not tracking the same x and k. We are tracking when do each processing elements get valid data, right? So in the 0th clock cycle, the first processing elements will get the valid data, valid x and k. And in the first clock cycle, the second, these two will get the uh, valid data. And then these three of them will get the valid data. And next, these three, and next this, and next this, and next this, right? So you can see this. So this is called a wavefront, right? The what I have drawn as this red dotted line is called a wavefront in a systolic array. Okay. So the idea is like, I mean, just like so the this sort of like it's similar to how waves travel, right? So you can see like in a big ocean or something, you have like a bunch of like the waves are moving from here to here, right? So you have waves that move from here to here, and so the first wave hits this one, and then after some time the wave hits here, and after some time the wave hits here, and then it hits here, and then it hits here, and then it hits here, like that, right? And you can see while the waves are moving, so when this wave goes here, now a new like a wave has come here, okay, and when this moves there, another one has come here, and like so it's basically shifting. So this thing is shifting downwards, right? Okay. So what we are looking at is the, as I told you, like these numbers correspond to in which clock cycle you are getting the valid data, right? So the first valid data, right? So the first valid data you are getting in the 0th clock, you are getting the first clock, you are getting the second clock, third clock, fourth clock, fifth clock, and sixth clock, right? Okay. But at the same time, so that is when you say the first valid data, that means what is the valid data here? So valid data here, because this is the R dimension, right? So, and R dimension is this one. So that means the first column of this, first column of A, right? That is the first valid data. Okay. And at the same time, like this is the C number of this number of columns is C. Okay. So, and the first row of this. Okay. So this and this are the first valid data. Okay. So this is 0 and 0. Okay. So that's when the like this data arrives here, right? And here. Okay. And what is the next valid data? So the next valid data is basically this one and this one. So they both arrive here. Okay. So when they arrive here, this very first valid data will move to this place. right? So when they arrive here, the first valid data moves here, and then when the next one arrives here, the first valid data has moved to this one, and then it has moved to this one, and it moves this one like that. Okay. So you can see how this data is sort of moving in a wave-like pattern through the systolic array, right? So a useful abstraction for this to have is basically, so now the question is we need to make this module access free, right? So how do you multiply and accumulate and everything, and when you get the result and all? So you want to make this module access stream. So why do you want to make it access stream? Because you want to put it on inside an SoC, system on chip, right? So so as we discussed, you get all these different IPs, and most of these IPs are in XE and XE stream. So if you make your module access stream, then it's very useful, right? So there are many ways of making this access stream. We can actually you can simply write it, but what I have written is sort of I wanted to make it a little more performant, in the sense I want to be able to do the matrices back to back and stuff like that. So how exactly I have implemented this is not super important. So in the sense even if you don't understand my particular implementation, it's completely okay, right? So I want you to focus on the SoC integration part, but I'm going to explain my implementation. So probably you can get something from that. But even if you don't understand it, you can still understand the SoC integration. That way you can integrate your own modules into our sort of harness, right? So that is the whole point of this workshop, right? But yeah, okay. So you can see this wavefront moves like this in every clock cycle, right? From 0, 1, 2, 3 up to 6. So what we can do is basically we can abstract this away as a shift register, right? That is, we want to track the valid data. Where is the first valid data going? First, not only first, and basically all the valid data. Okay. So, and then valid last and all these signals. So the input signals, right? So now we will assume, so we are here assuming this, the data that comes from here is an access stream. Okay. So, and this access stream data will have X is the row. So this one row, and then this is the K row, K columns. Okay, like this, one of this and one of this. Okay, so this is the length R and this is the length C. Okay, and we will get a packet, and this packet might be of K number of beats, or the K number of clock cycles or something. And this K can be a variable, we don't care, right? So, but as long as at the end, at the very last clock cycle, we get a last. Okay, we'll get a last signal. Okay, so as long as we get a last signal, we don't have to care about it. So this is the this is how we are getting the data as input. So let me show you how that maps to the Verilog code. So you can see, okay, yeah. So you can see SX data. So this is our so you are getting one column of it, and you have R number of elements. Each element is WX wide, right? WX is the width of X. And this is you have C elements, and this is WK wide, okay, width of K, okay. And then you have a S valid, S last, and you have a S ready that goes out, right? And on the M side, the master side, so you have R columns, and so you have, okay, that is basically I'm sending the data out like this. So I'm sending the data out like this. Okay. So all of this will go out in one clock, right? So one entire column goes out in one clock. So there is R number of elements, and the size of elements is Y, right? So that goes out with Y. So it's same data. Okay. So let's see how this is. Okay. Yeah. All right. So let's look at how we do this control signal part. So we have this S valid coming in, right? So S valid is the whether each beat is valid or not. Okay. So each clock cycle, each beat is valid or not. So we take this and you put it basically through a shift register, and the size of the shift register is D plus LM plus LA. So what are these? LM is the latency of the multiplier. LA is the latency of accumulator. Okay. And D is the number of diagonals. Okay. So how many diagonals are here in this particular systolic array? So you have 7 diagonals, right? So each of these wavefront, possible wavefront. So you have 0, 1, 2, 3, 4, 5, 6. So you have total 7, and that is your D, right? So, and then D plus LM plus LA, that is the entire number, it's a shift register size. Okay. So this is like an abstraction that I'm using, right? Okay. So now okay. So this S valid comes with this beat, right? So along with this beat, like this valid comes in the same clock cycle. Okay. So now let's take any particular diagonal D. Okay. So this diagonal can be like, I mean, let's take this diagonal. Okay. So let's say our diagonal D equals 2. Okay. So in this D equals 2 diagonal, okay, 0, 1, 2. In this D equals 2 diagonal, now this shift register is basically this like a D plus LM plus LA, very long shift register, right? And if you index into this shift register, okay, so if you index into the shift register and look at the second value, so that is D equals 2, okay. So if you look at this value, 2, okay. So now the value that you get, of the shift register, the output from the shift register here will be what? So that will tell you whether like the data that you are having here is valid or not. Your input data is whether that is valid or not, right? Because it is the S valid delayed by 2 clocks. Okay. And the clocks are going like this, right? So it's valid divided delayed by 2 clocks. Okay. So now if you look a little bit further, and if you do D plus LM in the shift register, and if you look at this point, okay, so if you look at D, you will get this xk valid, whether your input data is valid or not, whether this data is valid or not, you will get that, right? So if you wait for 2 clocks, if you wait for LM number of clocks further, what you will get is the M valid, or like, I mean, you can say multiply valid. Let's make it multiply valid. So okay. So if you wait for like another LM number of clocks, why? Because the multiplier has a now after D equals 2. So let me stop here. Okay. So you have D equals 2. So after 2 number of clocks, you have this xk valid. And then if you wait for LM, that is like what latency multiplier, then like this data will go through this multiplier and you will get an output here, right? So now you know whether that output is valid or not. If you wait, like if you look at the shift register's value at D plus LM, right? And if you look at the shift register's value at D plus LM plus LA, you will know whether the accumulator's value is right or not. Okay, valid or not, right? So that is A value. Okay. And then if that is valid, then basically you can, like, I mean, at some point you will copy that into a register, this register over here. And once you copy that, at the same time, you copy the value also into this R registers, and then you know whether that register's value is valid or not, right? So you're basically tracking which data is valid throughout the systolic array, right? So, I mean, one way of tracking that is you can probably track along this and this dimension, like in every cell, you can track whether the data is valid or not. But that is like too much of tracking. So what I'm doing is I'm tracking along this diagonal, because like it is along the diagonal, it's always very synchronized, right? So over here, so you can see this, what you have the zeroth wavefront, first wavefront, second wavefront. So at the second wavefront, you can, like, this is this and this are all in the same state. They're all valid. Like they if their multipliers are valid, then they all multipliers become valid at the same clock cycle. Accumulators become valid at the same clock cycle. Registers become valid at the same clock cycle, etc. Right? So because of that, it is much easier to just look at the valid along this diagonal without looking at individually. Okay, so that's what I'm doing here. So let me show that in the Verilog code. Okay, so this is the one I'm delaying our input by okay. So I'm delaying S valid. I'm delaying S valid by this many LM plus LA plus D number of clock cycles, right? And the output data, I'm getting them yeah. So this D corresponds to the output data, right? So I'm delaying it by that much. And then I'm looking at this LM plus D value to figure out whether the data is like first data or not, like in each diagonal, in any particular diagonal. Okay. So that way you can like there is one way of tracking data. Okay, through that. And similarly, I'm also doing like V last and valid and last. I'm delaying it through LM plus LA plus D and checking whether that is valid or not in every diagonal. Okay. All right. So right. So like any questions so far about like tracking the valid data and everything? Okay. So yeah. Okay. So the next one is basically this: how do we send the data out? Okay. So now we are moving this. The data moves like this, and as I said, we have the last signal S last, comes here, right? This last comes here. So whenever you get a last signal, that means you are done accumulating, right? Each accumulator, you keep accumulating until you see the last signal. And at that point, you are done accumulating, right? So then what you want to do is you want to copy whatever data you have into this internal register. So each PE has its own internal register here, right? So you want to copy the data into the internal register from quickly, right? So, okay, so that is this one. Okay, so each of them has an internal register and you copy the data into that, right? And once you copy the data into that internal register, you can continue doing your stuff. Like in the sense, now your accumulator is clear, okay? And as I said, now the next data is will be the first, right? So, and then because it's first, then you will like start from fresh, you into the accumulator and like you keep accumulating until you see the last signal, right? So that way, like, and you get like a new data, right? So that way you can keep doing that and your data will stay in the register, right? In the internal register. Okay. So now okay. So we want to shift the data from internal register to the output, right? So, but when can we do that? To do that, we need all these, like these four of these registers, or like all these registers along this output column to have a valid, like, um, to have a valid data, right? So the all these registers along this output column should have valid data. Okay, so that can be done only after accumulating in, like you go this and until you hit the very end, right? Until you hit this particular column. So, and then once that finishes, now you will have a valid data here. And when you have a valid data here, now you have valid data everywhere from here to here. And now you can shift that out. Okay. So, yeah. So once you have valid data here, we will start shifting. So how do you shift? Shift means like now you like when this one becomes valid, we say M is valid, right? So the output is valid. So then the like on the other side, like you will have your, I mean, you look at your ready, M ready, right? So if M valid and M ready, then what you do is you can like now this data, you can replace it with this data from here. Okay. So what we are doing is like these registers, then you have these registers. These registers will replace this. Okay. And similarly, everything over here will replace this. Okay. Or else, yeah, they are being copied like this horizontally. Okay. Why do we do this? Because like now all this data has to go out in parallel because the output is a XC stream protocol, right? So you can't sort of like move data sort of one by one or something. Like you have to copy everything at once, right? So that's why what we are doing it this way. Okay. And this also we will basically copy it what to here the same way. Okay. And this gets shifted out, right? So this way, like you are moving all this data to the to the right. And once you finish copying all the data out, so now like you are sort of empty, and then like you can accept the data from the accumulator. Okay. So, and we need to when you're copying the data out, we also have to track this the valid signals. So basically, this the like when this goes here, this valid should become 0. Okay, so then when this goes here, this should become 0, 0, 0. So finally, when everything goes out, everything will be 0. Okay, so that is one. And similarly, the M last, so this is m last equals 1, and then this gets shifted here, 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 and this goes out with m last. Okay, so and this becomes an accelerator cut. Okay, the green columns, they become an accelerator cut. So that's how we are sending the data out. Okay, so any questions about that? Can't we send them out row wise? So okay, row wise means you are saying like if you want to send the data like this, right? So basically you want to send this, okay, this first and then this first, the second and then this and then this. You can do that, but then it will be the pretty much the same architecture. The only difference is like this and this will be flipped, right? So there, I don't think there will be any performance difference or anything. So you can either send it this way or you can send it that way. What happens when there is invalid data in the accumulator? Will they consider? Also, is it necessary to track valid data always? Okay. So when there is invalid data in the accumulator will not accumulate, right? So yeah, so we have it over here. So that is like a really good question. So you can see here in the PE inside Mac. Yeah. So we only do the accumulation when this invalid is high. Okay. So invalid is like multiplier valid, not the output value. So whenever there's a multiplier valid is high, then only we accumulate the result. Okay. So we don't accumulate when that is not the case. Okay. So the accumulator will not be updated when the embedded is not like the multiplier is not valid. So the next question is like, also, is it necessary to track valid data always? So yes. So the thing is like, if you don't want to track valid data, you can, I mean, you can make a much simpler accelerator, but then you won't be like, I mean, what, and you can make it access stream the way I told you before. That is like, you can put like an enable signal for the whole thing and make it access stream. But then that will have the problem of like, you can't do back-to-back matrices. So here the idea is like the moment you are done with the previous matrix, you can start the next matrix as long as your data is shifted out, right? So if you are able to shift the data out, then like you can start the next matrix immediately, right? So okay, so yeah, the next one is if we send the data row wise, the data will be ready after the third wavefront, isn't it? Not really. So why do you say so? So if you are sending the data row wise, so right now we are sending like a one entire column at once over here. But if you are sending the data, what if you are saying basically we can shift the registers like this from top to bottom, and we can send it out from here. But then if you do that, you will still have the same number of delay, right? Because this is what we have here is sort of symmetrical between row and column, right? Yeah, yeah, exactly. All right. Okay. So about like is it necessary to track valid data always? So yeah, it is what if you want to do the like processing back to back, then it's better to track the valid data always. Okay. Or else, like, I mean, you can implement the same systolic array in different ways. So if you don't want to track the valid data, you can basically, you can probably stop the systolic array when there is no valid data. You can do stuff like that. But the thing is, like, your input data is going to have always invalid clock cycles. Why? Because like you are getting this data from an SoC, SoC DMA, right? And the DMAs can't always give you valid data in every clock cycle. So there might be like congestion, there might be what, like, I mean, the DMA is asking the memory for data and memory may not give the data in time. So for all of these reasons, there are like, will be some places where like, I mean, the data is not valid in the middle, right? For some clock cycles. So which is why we have the access stream protocol, right? Where like you mark which clock cycles are valid and which are not valid. Okay. How does the MLA signal get initiated? Okay. So the way that I am initiating MLAST is I am setting this one to high. So that is the zeroth. So I have a shift register here, and I am setting the zeroth shift register to high. And then like you basically shift that back and like through this to until the very end. Okay, so that way like MLAST always becomes I mean these all have zeros. These all always get zeros, and this first one will get one, and then like it gets shifted completely, and like you get like a one here only when there is the last. So that is like when this column goes out, it goes out with the MLAST one. Okay, and then like I mean once that is done, like what I reset this to one. So that way like yeah. So you always initialize this to 1000, and then like you shift it. Any other questions? Okay. Okay, one more. Yeah, LA means latency of accumulator. Yes. All right, great. So let me show the rest of the control signals. So um, okay. So yeah, once again, like you don't have to completely understand this, and like this is not the only way to like build a systolic array. So you can actually build a much simpler systolic array if you sort of like have valid ready signals for every PE or whatever, right? So that is one way of doing it. So here, like I'm trying like a different way of like tracking the data through the wavefront. So the along the diagonals. Okay. All right. So right. So you can see that okay. So these are the control signals. So M first. So M first basically tells. So M first D. That means in the Dth diagonal. So the diagonal can be 0, 1, 2, all up to 6 or something. And in the diagonal D, what happens is that so it goes all the way up to D, and in the diagonal D, M first is mm, yeah. So you initialize this to 1. So whenever reset, like you start this with 1, and then like what if for every valid, you only initialize it based on the V last, right? So the idea is like it will be if the next one is like last, then this one will be first, right? So like it works in that kind of a way. All right. So okay. So for the last signal, like you can see, like this is the registers, right? The R last register. Okay, so this is the one I showed here, the bottom. So which becomes M last. So the yeah. So the zeroth R last register, that is the first column, this one, that is tied to R valid. Okay. So whenever that particular columns become valid, then that last signal also goes high. Okay. So for everything else, for the other like Arla signals, okay, so you reset them to 0 whenever this happens, and then you shift it from the previous one to the next. Okay, so what is this condition? So when the M last is hit, okay, so one is like either D is greater than C minus 1. So that is like what now this these are 1, 2, 3, 4. Okay, and these register signals are also like sort of like along the diagonal, but I'm showing like this for simplicity, but you actually have a few more signals over there, right? Because you are tracking both the diagonal and the column with the same this thing. So yeah, and whenever you hit M last, that is like when you hit the last like the last out has gone out, you reset the signal to 0, and then otherwise you just shift from the left. So this basically becomes 1, and then it gets shifted all the way up to the end. And when it goes to 0, you basically reset everything to 0. That is how the last one behaves. Okay. All right. So, and the next one is like A valid. So this is whether the accumulator's output is valid or not. Okay. So this one again depends on the valid last. So this is V last is basically the S, the slave valid last. That is this one, S valid and last. This one delayed through a shift register. Okay, the same way. Okay, and then from that we can see if the accumulator is valid or not. How? We check this LM plus LA and D minus 1. Okay, so after that many clocks, then like the accumulator is going to be valid. Okay, so why D minus 1? Because here we are like copying that into the new one, right? Okay, so there is a reason. And yeah, so and over here we have the like okay, so now these things are there to check for conflict. So conflict is, I told you that we can do this like matrices back to back, right? So with this, so that means as soon as now this one finished accumulating, you can copy it into a register here, the output register, and then you can start accumulating the next set of matrices, right? Now, what happens when you finish accumulating the next set of matrices and you try to copy it into this register again, right? So now if the output has not moved out completely, okay, then you have a problem. Then now you have to stop the whole thing. Okay, so that is a stall condition, right? So you have to stop the whole thing. So you need to have, I mean, you have to check those things as well, right? So that is these are done to do that. Okay, and similarly, this is the R valid. That is the like the valid signal that goes out. And finally, you have is the R valid signal. M valid is the last R valid. M last is the of this one. Okay, and now this like the way you set like enable or disable the whole thing, you check for conflict. So if anything has a conflict, then you stop everything. So similarly, how do you shift? How do you shift the registers from left to right? So you do that when mvalid and mready. So when both are high, right? So then only the each shift happens. Okay. So these are like a bunch of control signals, and you don't really have to understand them exactly because you're not going to actually work with this systolic array. But the idea is like, I mean, there's one way of making it access stream. You can make your one access stream either way. So the way I showed you earlier last week, so that is a very easy way of doing it. But then, like, I mean, if your output has a variable number of what is that? What like your the number of clock cycles it takes to calculate something is variable. So here it's variable. Why? Because now I wanted to build it with this k clock cycles should be variable. That's the idea, right? So yeah. So if that is the case, then you can build it this way also. Okay. All right. So now this is the processing element, and we are basically getting the data from this. What this is the triangular buffer. So these three registers you see here, those are these try buffers. Okay, and I have the code for that as well. And so that gets fed into the processing element array. Okay, so this is for R in R and C. So like you have R into C processing elements, and you push the data and get them out, and you yeah. So there is the the entire systolic array. Okay. So do you have any particular questions? Anything about your design decisions and stuff like that? Okay. So yeah, let's move on to the access stream VIPs. So verification IPs. So and you can use these to do your own verification. So like if you are building access stream modules, then I highly recommend you to use something like this, or you can just use this as well. Okay, so I'll put the link in the chat. Okay, so let's take a look at them and see how they are. See how they are used. Okay, so right. So the idea of okay, let me show the test bench of this. So that way, like you can see how these get used. Okay, so the idea is like basically now we have this our systolic array. This is our systolic array design, and now we want to test not only that it does matrix multiplication. That is a functionality, right? So one is whether it does matrix multiplication, and the second one is whether it does like matrix multiplication over all the possible access stream combinations. So that is like if you stop and start access stream, like if you have a bubble that is like if valid goes down at any time, or if last comes after some time, or like all these different cases, right? So even if you stress the design a lot, then it should work in all the cases. So this is pretty hard to achieve, like especially when you are doing like designing this data flow like this way. Okay. So how do you do this? So to do this, what we have to do is something like um, we need a verification IP that can generate randomized transactions. So randomized valid and ready transactions. So that's what we have as this access source and access sink. Okay. So let's take a look at this source. So this is access source. So which means it sends data through this is ready, is valid. Okay, so it takes S ready and it outputs S valid, S last, and S keep and S data. Okay. Okay. So this is the task that is it like we push a packet. Okay. So the input of the task is basically a packet of each of word width of this. Okay, this many bits. And how many values like in the packet? It can be any number of values, right? Why? Because there's a queue. So queue means it's a dynamic array, right? So dynamic array, you can put any number of like elements you want into this, right? Okay. So, and once you pass that and call this task, so task is like a function, right? Instead the system verilog, a function that can take time, right? That's the idea. So now the total words is equal to the size of this packet. So that is how many what is that clock cycles, right? Mm, okay. Right. Okay. So yeah, this size basically I think gives you the number of bytes or something. Yeah. So it doesn't give you the yeah, it doesn't give you the actual number of what the beats. Okay. So the n beats is basic like you divide the total words divide by words per beat. So this is the what it's a parameter we give here. Okay. So what is a beat? Beat is the number of clock cycles that you get, right? Okay. So then we are sending this data through here. Okay. So all right. So what is this probability valid? Okay. So the probability valid is the probability of which the valid signal can go up or down. Okay. So the idea is like now before we start before we send one beat, okay, what is a beat? It's a valid clock cycle, right? Before we send a beat, what we do is like we generate a random number between 0 and 99, okay, that is inclusive. So the first 100 numbers, right? And then you see if that number is bigger than the probability valid or not, right? Over here. And if that is true, then basically you spend one more clock cycle and you keep doing this again and again. So by doing this, what we are doing is like we are waiting over here for a random number of clock cycles. Okay. So if you put this probability valid as 100, what happens? Now this will be like now the 100 is this this is immediately fail, right? So when you put probability valid equal 100, this will immediately fail because the U random range is like 0 to 99. Whatever number you get is not going to be higher than probability value, right? So this will fail immediately. Once it's failed, you will just continue and do the stuff. So if you put probability value equal 100, we will not wait at all. We will never wait. Okay. But if it is, say, for any other number, say 99 or 20, 30 or whatever, then the time you spend here will be proportional to the how do you say that? Like it's sort of like inversely proportional to the probability, right? So if you put zero, then that zero will be sort of like always, you will never get the, wait, if you get zero, mm, yeah. So if you get zero, then this will be always true. So it's like a while loop and you will keep on going into this. You don't want to do that. But for any number of values, say 20%, 30%, 40%, then you will wait for that percentage of like, say, it's a random chance of you will be waiting for certain number of clock cycles, right? So the idea is like if you look at if you run the simulation for a long time, okay, and after before every valid beat, you are waiting for certain number of clock cycles, and the percentage, like I mean, the probability of like you are waiting will be that many percent on average, right? It will be sometimes more, it will be sometimes less, it will be fast, it will be slow, and etc. etc. But then the idea is like I mean, you are what you can control the variability by this one parameter of probability, right? If you set it to 100, then you get like a complete data flow without any without any like the valid never going down, right? So that is sort of like the ideal data flow. Like I mean, that is what we want. In the sense, you want to push data 100%. But then we know, like in an actual system on chip, the data is never going to come like that. It's never going to come 100% valid, right? 100% all the time. Why? Because there's bus congestion and there's like you have other issues. So whenever that happens, this valid has to go down to accommodate for that. Okay. So that one we control it by prob valid. By adjusting this, we can stress test the design for different cases. Okay, that is the idea. Okay. So after waiting that many clock cycles, then we continue. And over here we iterate over the number of words per beat, in per beat how many words, and we send the data as well as we put the packet into the data, and then we also send the what a keep signal as one. Okay, and we keep like incrementing the number of words that we have sent already. Okay, right. Okay, so the last signal over here, yeah. So the last is basically IB equals to number of beats equals -1. Okay, so number of beats. So based on that, like yeah, so we keep going like that, and then like so once we put the data, okay, and then we have to wait for a string. So as I told you in access stream, we can't change valid or data when SRD is down, right? So you have to hold it steady. So here by the protocol, we are waiting for the handshake, okay? And then you go around and around. Okay, so yeah, and there's also this helper function which reads a given file into a queue, right? So I'm using this to like if you want to read the data from some file or something, then you can do that. Okay. So similarly, this is access sync. This is the output port, right? So this connects to the master port of your design, right? And it has a task called access stream pull packet. So it pulls the data from your module and converts that into a one packet, which is a queue, and it gives you the queue, right? So that's how this works. Okay. So like again, what we do is basically we change this ready random. Okay, the same way we change valid, we change ready randomly, and with a certain probability. And then like whenever like we are continuing here, we if it is valid, okay, then we copy the data from that comes from your module. Okay, and then we like go back in a while loop and then wait for random number of clock cycles and see if it is valid, then we do this. So this way we keep doing it again and again and again, right? Okay, so this is a sync module. So that is like yeah. So how do you actually use these? So you use them like this. So you use the source and sync like this. Okay, so let me see. So initial begin. Okay, Mm, okay. So, right. So I have now three initial blocks. Okay. So in system log simulation, like all these initial blocks, they start in the same time. So this is it's like you can think of it as some sort of like a multi-threaded code or something. It's not actually multi-threaded, but then you can think of it like that way. So this, and this, these three initial begin, they start at the same time, right? In parallel. Okay. And yeah, so the first one, it sends the source, what um okay. So it creates a random queue. Okay. So that is like it generates random data. So this also I have it in here. Okay, get random queue. So this function, if you give a certain like integer, so I want this many words. Okay, it creates that many words, and it creates that many random words, right? And it puts it back into like the queue and gives you the queue. Okay, all right. So that's what I'm doing here. I'm creating a randomized queue here, and then I'm putting the randomized queue, and I'm pushing that. I'm calling this function. So this task, and this task basically runs the what it acts as a master. So, and it gives you this randomized queue through the what port, access string port. Okay, and once you are done, it will give the last also. So this is how you drive the port. Okay, so similarly, k is the weights. Again, I'm creating a randomized packet, and I'm driving the packet over here. This happens over multiple clock cycles, both. Okay, all right. And now this is the part where the monitor where you check if the data is correct or not. Okay. So what you do is sync Y. So on the sync side, you are pulling a packet. Okay. So Y packets in. So you read a packet, and once you get the packet, so E packet is the expected packet, right? So now I'm taking this K packet and X packet. So the K is the weights and X is the what input, and I'm doing a matrix multiplication myself here. So that is C equals 0, R equals 0, and then K equals 0. This is a triple nested loop of matrix multiplication. And you multiply everything and then like push it into this E packet, expected packet. And then you compare whether these packet match. And if they match, then you say, yeah, they match. Otherwise, you say that there's a failure, right? So, and this is how you use this, what is it? The VIPs. So you can see they are like pretty simple. Like you can create randomized packets and you can push them, and you can you can even read from a file and push them. So I recommend, like, I mean, if you want VIP to test your designs, then you can use this. So you may ask, like, why do I? So when you run this one, when you run make very axis, this is what you get. So all this data has gone through and got out and they match. Okay. So if you ask why do you need this, or in a sense, why do you need to test, stress test the design with these different valid probabilities and ready probabilities and everything? So then the answer is, if you don't do this, so let's say you are building a design. So maybe like your final year project or accelerator, or like maybe in your company, you are building some sort of accelerator, video decoder or something. Okay. So you have some design, and then like you test it for a couple of cases. You don't like without this kind of a transactional test bench, so you can test it for some cases. So I have a smoke tb here. So the smoke tb test is like that. So I'm sending some data, then waiting for some clock cycles, getting the output and comparing it, right? So that is the simple tb, right? So if you're just using the smoke tb, and now you check a couple of cases and all of them pass, and now you go and put that in a fpga, or you put it on a, like, I mean, what you will put it on FPGA, and then you run the design, it's going to fail immediately. Why? So, I mean, it might pass like a couple of times, and then like one day it's going to fail. And then, like, I mean, it's very hard to debug things inside the FPGA, right? So you have to put the ILA in a simulation or something, like, or else like, or you have to put the ILA and like see when it happens. So sometimes when you put a ILA, it doesn't happen. So like it's a huge pain to like debug a problem in an FPGA. And if you spend a lot of time and you figure out why, then it will be in a very corner case when your valid goes down in a certain clock cycle, your output, like I mean, your design goes to a weird state. Okay, so your design sort of hangs in a certain weird state, and then like I mean, you are not getting outputs. So this is very common. This happens all the time, right? So to prevent that from happening, what you do is like you have to build a test bench like this, which test your design. Okay, which can raise and pull up valid up and down at all possible configurations in different ways. So that way you test your design as much as possible before you put it on FPGA. So that way you can get it working pretty quickly. Okay. All right. Any questions about this? About how to use this test bench, this VIP, or how this VIP works? Okay. All right. So yeah, let's move on to the next one. There are no questions. Okay. So the next one is like the firmware. Okay. Access SATB. Wait. 97 to 102. Okay. 97 to 102. Okay. Yeah. So this is basically you are checking if the expected packet is same as the output packet. Okay. So the idea is like now, so here we are creating a random input packet and a random weights packet, right? So, and now we have to see if our like systolic array actually does matrix multiplication. Okay. So to do that, what we do is like, and we are sending n number of packets here. Okay. So these are yeah. Okay. So we have n number of packets. So this n is number of experiments. So number of experiments, that many packets are there. Okay. So, so what we do is basically over here, we pull like from the output, we pull a packet. Okay. So this Y packets in, that is the actual output packet, right? So now what we do is we create this E packet. E packet is the expected packet, which is like, I mean, and how do we create it? We do the matrix multiplication. We take the randomized, like the packet that was previously sent, that is the K packet, and then the X packet, and we do a matrix multiplication. And this is the matrix multiplication code, right? So, and we put the result in the E packet here. Okay. So, and now, like, if our design is correct, then this E packet should exactly match the Y packet, right? So that is what we are checking here. So if they match, then we print, okay, outputs match. So that is what it's printing here. So packets one, outputs match and everything. Okay. So otherwise it will say like, I mean, this is this packet and what for this particular number of index of packet, this is the expected packet, this is the received packet, and they are not matching. Okay. So that's what it will print. Questions? Okay, great. Okay. So, all right. So now let's look at our firmware stuff. So, right. Mhm. Okay. So that is our full system is over here. Okay. So this is our first full system, and like let me show you the firmware, and I'll show you where they map. So in C firmware.h. Okay, right. So what we have in this firmware.h, it is the actual file that this is the this run function. Okay, so this is the one that actually runs the what this is the function that actually runs the systolic array, right? So as we talked last week, so we need to like the way the whole thing is controlled is from the DMA controller, right? So we have the DMA controller over here. Okay, so let me go back and show you the entire diagram, sort of like then. Okay, now this is our entire diagram, and tomorrow we will see how to connect this to IBX SoC and everything. Okay, so in this diagram, this is the systolic array, right? So, and we have a access stream synchronizer here. I'll show you now. So, okay. So this is, I mean, what I call like a synchronizer. So the idea is that you have two independent access streams, right? So one is the this is valid what k valid theme, right? That is the what the k weights matrix, and the other one is the x, that is your input matrix. So you have two access streams. So now question is like now you have to merge them into one stream to give it the systolic array, because the systolic array takes only one stream as the input, right? So how do you like merge them? So the way you can merge them is like is valid. So that is the streams, like when you the merge stream is basically the k valid and x valid, right? And the other thing is like the ready. Okay, so this ready it has to go like this. So let me show you here. Okay, so you have two streams coming like this. Okay, so this is x and this is k, and you synchronize these two and you send it out as say sk and sx and sk, and you send it as s, right? So the valid is basically both of them ended. Okay, and ready signal goes from s to here. The ready signal goes from here to here, right? So what is the ready signal for this? Okay, so what is the ready signal for this? So that comes from whether this is ready and whether this is valid. Okay, so let me put that in a different color. See if you can, yeah. So you have a ready signal going back. So that tells whether the data is accepted or not. Okay, and that is, you have a ready signal coming here. So this ready signal is this one and this one. Okay. Why? Because that is how, like, if this SK is not sending data, okay, so if this one is not valid, then we want SX to wait until this SK starts sending data. There is a synchronization, right? So we want this both data to come at the same time. So then only you can put them together and send it to the what on this side. Okay. So this ready is equal to this valid and this ready. Okay. Any questions in this? What is the middle block? Okay, so there is no block. It's basically like, I mean, uh, this part. That is this. So if you can understand like the ready and like how we merge the ready and both valid. Okay. So all right. So yeah, we basically synchronize the K and extremes like this, and we send it to the systolic array into this. And similarly, we get the output here, and we get this partial stream from like partial sum stream. Okay. So why? Because like, so usually when you do this matrix multiplication, like what you're multiplying is actually a part of a big matrix. It's a tile of a big matrix, not the whole matrix, right? So you take this one tile and then you add the partial sum. Okay. So and that addition is done here, and then like you put it back. You add it with the output of the systolic array and you put it back, right? So and again, like you have two separate axis streams and you have to synchronize them. So that addition part is done here. This is the addition in Verilog, right? So and this here we are adding them together. Okay. All right. So yeah, and then we have this adapters. So and so this is sort of like the entire logic of this. Now let's look at these things. So these are axis stream adapters, right? These three of these. So what does that mean? So that means like these can change the width of an axis stream from like any size to any size. Okay. So the idea is like now what now a systolic array, we want the systolic array to be parameterized, and it is parameterized. That is R into C, right? So R rows and C columns. And the widths are also parameterized. So it can be 4 bits, 8 bits, and different widths, right? So now if it is say and 8 bits, let's keep it simple. And R can be, I don't know, like 6, R equals 6, and C equals can be 12 or something, right? So this is 6 bytes and 12 bytes, right? But then the DMAs usually don't accept such, I mean, like all kind of sizes. And then like, I mean, when you're reading data from memory, that's a bit harder and all of that. So what we do is like now the IP, that is like whatever we get on this side, okay? So we keep this in a standard size. So we keep this at 128 bits, okay? So 128 bits is like 128 by 8 is 32, I think. No, so it's not. 128 by 8 is 16. Okay. So this is 16 bytes wide. Okay. 16 bytes wide. But then the columns are 12 bytes and the rows are 6 bytes. So how do you convert this 16 bytes to 12 bytes and 6 bytes? Okay. And you have to convert this in a parallel way. That is like you have this data is like 16 bytes wide. Okay. And it's coming as a stream. And this stream, we have to arrange it to have like 12 bytes. Okay. So, and now this one is like, it is much more like, it's not very trivial how you do that. You have to put it into some shift registers and you have to manage the keep signals carefully. And you have to have the loss signals and like everything carefully. So all of that. So to do that, we are using this, adapter. Okay. So this is what we call the, access stream adapter. Okay. So these are from if you control click, you can go there. Okay. So these are from LX Frankic and these are access stream adapters. So we are using that to convert the 16 bytes to 12 bytes. Okay. So then after doing that, like on this side, now we have this 16 bytes. 16 bytes. And here we have 16 bytes, 16 bytes, 16 bytes. Okay. So there is 128 bits, let's say. So now we can put that through the DMA. So these are like the read DMAs from LX Frankic, and this is the write DMA from LX Frankic. So, and this is connected to that. So let me see, they are connected like this. So you can see the, MM2S DMA. Okay. So this is the Verilog DMA I said. So like you don't need to use the Xilinx DMA that has like a bunch of problems. It is it takes too much area and it is low performance. It doesn't have any advantage actually. So, and it's vendor locked. Okay. So instead of that, you can just use this DMA, this Verilog, you can just put it on like instantiate it. Okay. So you have like a lot of signals. It might look scary, but it is very easy to use. Right. So, and you can control it from from Verilog as well. Okay. So you have all these 4 DMAs on this side. Okay. And so how do you control the DMA? So for that, we have our own DMA controller here. Okay. And now, so let's see how the DMA controller works. Okay. So this is the register file I showed you yesterday, right? So this is very similar to the register file I showed you. So, and this has a register port inside. So it has like, I mean, I'm getting the data as a simple register port. So, and I have defined these register addresses, like I told you like last week. So we have the, what each DMA done, address, bytes, and the user, right? So, and over here, I'm basically putting this, so this register is the address for the first DMA, and this is the number of bytes for the first DMA. So you concatenate them together, and that becomes a descriptor, and you just give that to the DMA, right? So, and you have to give it as an access stream. So, and like basically you set the valid based on the like ready and this. Okay. So this way, like you have these 4 DMAs, you can control them from Verilog. It's very straightforward, just like this. Okay. All right. And then you have, So now this DMA controller has this register port. And I told you last week, this register port, we use this XE Lite to RAM module and XE to XE Lite module. So that way your input is an XE Lite, XE. So let me show this. So over here, yeah, so this is an AXI port, AXI slave port, and then we convert it to a AXI light port here. And then from there, like, we use the this AXI light to register module to convert it into register port. And then we have our own register file here inside here, right? Okay. So, okay. So let's see how we are controlling stuff. Okay. So now you can see in the DMA controller, the same address over this one is the one here, right? So, and this is C code and this is Verilog code, and these macros have the same values. So when I write to CFG plus this, it actually writes to the second register here. Okay. Okay. So what I'm writing here is the pointer of this variable K, the matrix K, right? So I'm writing that into this one. And similarly, the pointer of the X matrix, the pointer of A matrix, and pointer of Y matrix. So where are these actual matrices? So they are defined over here. So let me see where is config. Okay. So you can see this is the type def like struct. Okay. So like it's a struct of 1, 2, 3, 4 matrices, and this is the input matrix K, X, A, and Y. Okay. So these types are again like they are what uh, like they are defined based on the number of bits you set. Okay, in C. So I mean I have said by default they are like 8 bits, all of them, and this K matrix, it has what K rows and C columns, and the X matrix has K rows and R columns. So and then you have like this and this and this, right? So and what you do is basically you load you put the address of each of these. Okay, you write the address of that into this register, and similarly you write the size, how many bytes into the next register, this register. So similarly for this, the first DMA, zeroth DMA, first DMA, second DMA, and third DMA. Okay, so you set the address and the number of bytes. You set all of that, and then you set the start register to 1. So when you set the start register to 1, here you will detect that, and yeah. So when yeah, so when this happens, then the S2MM, all these valid signals go high, and when the valid signal go high, this the descriptor goes to the DMS, and the DMS will start working, and the DMA will push the data in and pull the data out. So that's how the whole thing works. And here we have a while loop, and we are reading this register again and again until you finish. Okay, so S2MM done. Okay, so and this is how you run the firmware. So to run the whole thing, you can do make very. Okay. Do you have any questions? Could you please explain how the matrices are placed inside the memory? Okay. So Okay, so yeah, I think that's a pretty good question. So yeah, and it's a pretty important question as well. So there's a key difference between not real difference. Okay, so in C, okay, so in C you have something called the um, column major, right? Column major layout. So that is a standard layout in C. So when you have a multidimensional array like this, K into C, okay, then what happens is like the way this is stored in the memory is that if you, let's say we are looking at this X, okay, let's say we are looking at this X, you start here, okay, now you will have continuously you have some these R elements, okay, so you will have R elements one after the other, okay, so this is the one that is stored next to each other. This is the one that is stored next to each other. And then you have another R elements. And then you have another R elements. Okay, like that. And that is your K. So how many of these blocks you have? That is your K. Right? And this makes sense, right? Like how do you address memory in C? The way you address memory in C is like you X. So you say what is it? Um, like 2 and maybe 3. Okay, this is how you address it. So when you say 2, 3, so what you are doing is you are addressing the third element here, and like you are addressing the second element over here. So that is, this is 0, this is 1, and this is 2. So let me put it in yellow. So this is 0, this is 1, and this is 2. So you are addressing this second element. So like basically this one. This is what you are addressing. Okay. And then you are addressing the third one within that. So inside here, this is 0, this is 1, and this is 2. So you are like, and this is 3. Okay. So you are addressing this element. So this corresponds to this. You understand? So, and then like when you do the DMA, okay. So what you do is like you tell the DMA that this is your pointer. Okay, this is where you're starting to read, and you ask the DMA to read it. Read what are you asking to read? How many bytes? The R into like R into K into the data bits, right? Like that many number of bytes. So basically, it's something like this. And the DMA will start from here and will give like XC burst and everything, and it will just read the data from here and send it. And then like the data with adapter will rearrange your data like into R sized data. And what you will get on your systolic array is you will get all these R elements in parallel in one clock cycle, and you will get the next R elements in the next clock cycle. Okay, that's what you get in the systolic array. Any questions? Okay, okay. So yeah, do we need any padding? Um, so in the default case, you don't need any padding. So like I haven't actually supported like bits less than 8. So if you are doing that, then you need to pad them to 8 bits or something, or else you can pack them together, or you can do stuff like that. I mean, but that is all on the C side, not on the systolic array side. But right now, you don't actually need padding for this. Yeah. Okay. All right. Any other questions? So on how yeah. So this is basically how the C and DMA controller and XC and all of this work together to push the data in and read the data out. Okay, so I highly recommend you to clone the Docker and try it yourself. Okay, so yeah, tomorrow we can do the IBEX integration and you can take a look today as well. And then if you have any questions, you can ask me tomorrow and I can answer you as well. Okay. All right. Thank you. Thank you so much.